The surface area of a solid object is a measure of the total area that the surface of the object occupies. The mathematical definition of surface area in the presence of curved surfaces is considerably more involved than the definition of arc length of one-dimensional curves, or of the surface area for polyhedra, for which the surface area is the sum of the areas of its faces. Smooth surfaces, such as a sphere, are assigned surface area using the representation as parametric surfaces. This definition of surface area is based on methods of infinitesimal calculus and involves partial derivatives and double integration. A general definition of surface area was sought by Henry Lebesgue and Hermann Minkowski at the turn of the 20th century. The work led to the development of geometric measure theory, which studies various notions of surface area for irregular objects of any dimension. An important example is the Minkowski content of a surface. In chemistry, surface area is important in chemical kinetics. Increasing the surface area of a substance generally increases the rate of a chemical reaction. For example, iron in a fine powder will combust, while in solid blocks it is stable enough to use in structures. For different applications, a minimal or maximal surface area may be desired. In biology, the surface area of an organism is important in several considerations, such as regulation of body temperature and digestion. Animals use the teeth to grind food down into smaller particles, increasing the surface area available for digestion. The epithelial tissue lining the digestive tract contains microvilli, greatly increasing the area available for absorption. Elephants have large ears, allowing them to regulate their own body temperature. In other instances, animals will need to minimize surface area. For example, people will fold their arms over the chest when cold to minimize heat loss. The surface area to volume ratio of a cell imposes upper limits on size, as the volume increases much faster than does the surface area, thus limiting the rate at which substances diffuse from the interior across the cell membrane to interstitial spaces or to other cells. Indeed, representing a cell as an idealized sphere of radius r, the volume and surface area are, respectively, V equals 4/3 pi r3, SAR equals 4 pi r2. The resulting surface area to volume ratio is therefore 3r. Thus, if a cell has a radius of 1 micrometer, the SAR-V ratio is 3, whereas if the radius of the cell is instead 10 micrometers, then the SAR-V ratio becomes 0.3. With a cell radius of 100, SAR-V ratio is 0.03. Thus, the surface area falls off steeply with increasing volume.